Good morning. I am Dr. Niti Maheshwari, Assistant Professor, Applied Science and Humanities Department, Ajay Kumar Garg Engineering College, Ghaziabad. Now today I will be taking the second topic of spectroscopy, that is IR spectroscopy, also known as infrared spectroscopy. Now this spectroscopy, it is used for finding out the structure of a new compound or to identify the structure of two compounds. A new compound can be identified, or two different compounds can be identified whether they are same or they are different. Now, coming to what exactly is IR spectroscopy. Now, this spectroscopy, it deals with the IR region of the electromagnetic spectrum, and it involves transitions between the different vibrational energy levels. Now, vibrational energy level, in the starting lecture in the introduction I had taken, they can be translational movement, rotational, vibrational, and then electronic. Electronic spectroscopy I have already taken, that is the UV. Now, the vibrational energy levels can change. When I give energy to the molecule, first it starts translational, then rotational, and then vibration. So, these IR graphs or the absorption peaks, they are obtained as vibrational rotational spectra. Now, this IR spectroscopy, the region lies between 4000 to 625 centimeter inverse, that is from 2.5 to 15 millimicrons. And the IR spectroscopy, it measures the bond vibration frequencies in a molecule, and it is used to determine the functional groups. What I mean by bond vibration frequencies, two atoms, they are joined together by a bond. When I provide IR energy to this molecule, the bonds, nothing is static, the bonds, they start vibrations. As a result, the bond which is present between the two atoms, it starts to stretch and relax on putting it in the IR radiations. So, there are bond vibrations taking place. The IR spectra, it can be used to provide information on the functional groups as well as the structure of the molecule, because in the functional groups generally we have an heteroatom. So, a bond between oxygen, nitrogen and the carbon, since there is difference between the electronegativities, so the bond stretching frequencies will also be different, or they are going to be very clear in the IR spectra. Now, what are the conditions for the IR absorption? First, the IR causes a vibration if there is a change in the dipole moment during the vibration. That means homodiatomic molecules like H2N2O2, there are no vibrations which can bring about the change in the dipole moment. During the course of the vibration, dipole moment does not changes, therefore, these molecules are IR inactive. Or in short, we must say that the molecule, they should not be centrosymmetric, the molecules which contain center of symmetry, because in that case during the vibrations or the dipole moment of one end of the vibration will be same as the other end of the vibration. So, if it is centrosymmetric, it contains center of symmetry, then generally those vibrations where center of symmetry arises, then they are going to be IR inactive. Those vibrations are going to be IR inactive. But homodiatomic molecules, they are completely IR inactive. They do not give IR absorptions. Now, the frequency of vibration, it must satisfy the rule E is equal to h nu, because specific amount of energy is required to bring about the change it must satisfy E is equal to h nu. Then the natural frequency of vibration of the molecule must be equal to the frequency of IR radiation. The frequency at which the molecule is vibrating, it should match the frequency of the IR radiation. Only then an absorption peak is obtained in the IR spectra. Now, this is the IR spectrophotometer which I am showing. We keep the sample inside, a computer is attached which can and where we can study the spectra. Now, the IR spectrometer, it determines the wavelength and absorption of a sample in the IR region of the electromagnetic spectrum. So, IR region, whatever absorption is being caused in the IR region, that we can study in the this spectroscopy. Now, coming to the principle of IR spectroscopy. In any molecule, it is known that atoms or groups of atoms are connected by bonds. When atoms they form molecule, then it is through the bonding. Now, these bonds, they are analogous to spring and they are not rigid in nature. The bond between the two atoms, it is like a spring. Because of the continuous motion of the molecule, because nothing is static, they maintain some vibrations with some frequency characteristic to every portion of the molecule. This is called the natural frequency of vibration. Now, the IR absorption, it is affected by the strength of the bonds, then masses of the atoms and the arrangement of atoms in a molecule. So, if masses increase, then they are going to affect the IR absorption in the IR spectra. If bond strength increases or decreases, again they are going to show different absorptions, and whether the molecule they are symmetrical arrangement or they are unsymmetrically arranged atoms in a particular molecule. Now, we can determine the stretching frequency by Hooke's law, and it says that stretching frequency, this is wave number which is inverse of wavelength. It is given by 1 upon 2 pi c, where c is the velocity of light, in f ma plus mb by ma mb, or where f is the force constant which is nothing but the strength of the bond and mu is the reduced mass. So, the vibrations they depend upon the force constant and the reduced mass. For example, if I take C single bond C, C double bond C, C triple bond C. Now, as we can see that the number of bonds are increases. Since the number of bonds are increases, that means bond strength is going to increase. When bond strength increases, the value of this force constant which is in the numerator, it increases. And when this F value increases, it increases the wave number. That means more wave number. And second is the reduced mass. How this reduced mass is affecting the frequency, stretching frequency. For example, if I am studying a bond between reduced mass, masses of the atoms. Atomic mass of carbon is 12, oxygen is 16. Again oxygen is 16, hydrogen is 1. Now, in this case, you can see that Ma plus Mb by MaMb divided by Ma plus Mb, that is the value of mu. Now in this case, since the masses of the atoms is more, therefore nu, which is in the denominator, this equation finally becomes F upon mu. Now this mu has to be small. Now in this case, mu, which is MaMb upon Ma plus Mb. Now here you can see the masses of the atoms is high, therefore the denominator will also be high, and in this case you can see that the masses of the atoms are less in comparison to the other one, therefore the value of mu will also be less. So value of mu, it becomes, in this case you can see the value of mu will become less in comparison to the CO. So lesser is the reduced mass value of mu, higher is the value of stretching frequency, and more is the reduced mass, then lower is the value of stretching frequency. So for higher stretching frequency, our force constant should be more, the numerator should increase, and reduced mass, the denominator should decrease. Now, when energy in the form of IR radiation is applied, and when applied IR frequency, it is equal to the natural frequency of vibration, the vibrations at which are taking place in the molecule, and when the one which we are giving through the our source. So when they match, then it will lead to the generation of IR spectra. Now here I have shown cation and anion, the vibration of a diatomic molecule, and it approximates an oscillating spring. It is a spring, it is not a rigid structure, it is like a spring. Now coming to the fundamental vibrations and their different types. Now the vibrations which are taking place, they can be divided into two broad categories. They are the stretching vibrations and the bending vibrations. Stretching vibrations are such that the bonds, they stretch and relax, but there is no change in the bond axis. And in the bending vibrations, different forms of bending, in that case the position of the atoms, they change with the original, with respect to the original bond axis. So such type of vibrations are bending vibrations. And since their bond is like a spring, so we require more energy to stretch a spring in comparison to a bend spring. Therefore, stretching vibrations, they are seen at higher frequency side, whereas bending vibrations, they are seen at the lower frequency side. And we are going to concentrate more on the stretching vibrations. Now these stretching vibrations, they are of two types: symmetrical stretching vibrations and asymmetrical stretching vibrations. Similarly, bending vibrations are of two types, one in plane bending vibrations and then out of plane bending vibrations. In plane bending vibrations again are of two types, rocking and scissoring, and out of plane are of two types, wagging and twisting. I will discuss in the next slide. Now, coming to the stretching frequency or vibrations. Stretching vibrations, they are of two types, symmetric stretching. Now in case of symmetric stretching, when there are two atoms joined to a central atom, then the movement of these two atoms with respect to the central atom is in the same direction. That means at the same time both the atoms are going to move away from the central atom, that is the bond will get stretched, and at the same time they are going to come nearer to the central atom, that is the bond is going to relax. So simultaneously they will move away and then they will come closer to the central atom. So that is the symmetric stretching. Asymmetric stretching, Asymmetric stretching takes place when these two atoms which are joined to the central atom, when one atom moves towards the central atom, it gets attracted towards the central atom, the other atom moves away from the central atom. Now, in this case, this atom is moving away, whereas this atom is moving towards the central atom. So, when one bond is compressed and the other is stretched, then in that case it is known as asymmetric stretching. Now, bending vibrations. These bending vibrations, they are such type of vibrations which consist of a change in bond angle between bonds with the common atom. When two atoms are joined to a central atom, then the bond angle is going to change. In other words, the bond angle changes, but the bond length remains the same. The bending vibrations, they can take place within the plane or out of plane. Now, these bending vibrations, they are of four types: scissoring, rocking, wagging and twisting. Now, coming to first to rocking and scissoring. When the two atoms which are joined to the central atom, their movement is in the same direction. When two atoms are joined to the central atom and both atoms, they move in the same direction, then it is said to be the rocking movement, and it may be on this side or this side. And the other case, scissoring, just like a scissor works. When two atoms are joined to a central atom, then the movement of the atoms are like this, they are moving towards each other and then away. So, both the ways they are going to take place. So, this is the scissoring, that is the two atoms, they approach each other. So, here again rocking movement, scissoring is towards each other. Wagging is when the two atoms joined to the central atom, they move above and below the plane simultaneously at the same time, then it is wagging. So, when the two atoms join to the central atom, they are moving above the plane or below the plane at the same time, then the vibration is said to be wagging. And twisting vibrations are such, when these two atoms which are joined to the central atom, when one atom moves above the plane, the other is going to move below the plane. So, such vibrations are called as twisting vibrations. Now, coming to the number of fundamental vibrations. When a transition takes place from E is equal to h nu, from ground state to the first excited state, then such vibrations are called as fundamental vibrations because they absorb light strongly. A molecule can vibrate in many ways, and each way is called a vibrational mode. And the number of fundamental vibrations, they depend upon the structure of the molecules. For a linear molecule, the vibrational degree of freedom is 3n minus 5. And for non-linear molecules, the vibrational degree of freedom is 3n minus 6, where n represents the number of atoms in a molecule. Now, how do we calculate? The total number of vibrations which can take place in a molecule are 3n, and this 3n is comprises of translational, rotational and vibrational. 3n is of translational, rotational and vibrational degree of freedom. Okay. Now, here since translational is always 3, x, y and z axis, along z axis, therefore, translational degree of freedom is always 3. And for linear molecules, there is going to be movement in only two directions, that is x or y, or x or z. So, therefore, there are 2 degree of freedom for rotational, and this is v, So vibrational degree of freedom for linear molecules become 3n minus 5. Similarly, for non-linear molecules, our translational is 3 and rotational also can take place in 3 directions. Therefore, vibrational becomes 3n minus 6. So, here for non-linear molecules, the total vibrational degree of freedom is 3n minus 6. N is the number of atoms. So, we can calculate how many vibrations are going to be IR active, or how many vibrational peaks we are going to get in the IR spectra. How? Now, I have taken the example of CO2. Now, this carbon dioxide molecule, it is linear and it has 4 fundamental vibrations. How? Linear molecule, and you can see here for linear molecules the vibrational degree of freedom is 3n minus 5. In the case of CO2, there are 3 atoms. Therefore, 3 into 3 minus 5 is equal to 4. So, there are going to be 4 vibrations which we must see in the IR spectra. But is that so? We will see. Now, here the carbon dioxide molecule, it is linear and it has 4 fundamental vibrations. The first is the stretching vibration, which is symmetrical stretching. When the 2 oxygen atoms, they are going to move away from the carbon atom at the same time and come near to the carbon atom. Then the asymmetrical stretching, when one atom moves towards the carbon, the other is going to move away from the carbon atom. Then this is scissoring direction, carbon and oxygen and carbon and oxygen. So, they are overlapping ones. Now, here in the first case you see, so by calculation we have calculated that there should be 4 theoretical fundamental bands which are expected, but actually it shows only 2. Why? See the first case, symmetrical stretching. Both ends are oxygen and there is center carbon. So, electronegativity at both the ends of the chain oxygen is same. So, when the symmetric stretching will take place, this stretching will not bring about any change in the dipole moment during the course of the vibration. During the course of the vibration, our dipole moment should change. That means the dipole moment of one end should be different from the other end. But since there are same atom, therefore they are going to stretch and relax the bond in the same manner. Therefore, it will not produce any change in the dipole moment. Therefore, this vibrations will not be seen in the IR spectra. Asymmetrical stretching will be seen. And this scissoring CO2, since they are same, scissoring, when they are going to move here, the carbon atom will move above, or when the carbon atom moves below and they are going to, oxygen will move up. So, scissoring, both they occur at 667 centimeter inverse. So, they are going to overlap with each other. They are not going to behave like 2 different vibrations. These 2 will overlap with each other, though they are going to show only one vibration. Therefore, the symmetrical stretching vibration in carbon dioxide is IR inactive because it does not produce any change in the dipole moment of the molecule. And the second, the 2 bending vibrations, they are equivalent, they are same and they absorb at the same wave number. That means they are going to overlap with each other. So, only one peak will be shown. Now, in IR region, it is studied in 2 parts. The first part is the functional group region, where we can find out the different functional groups which are present in the organic compound. Now, these peak in this region, they are characteristic of the specific functional groups which are present in the organic compound, and this region, it lies between 4000 to 1300 centimeter inverse. So, all the functional group peaks, they are going to come between 4000 to 1300 centimeter inverse, and the different functional groups, they absorb at characteristic frequencies in this region of the spectrum. Every functional group has a characteristic absorption position in this region. So, we can differentiate which functional group is going to be present. For example, CO group. CO groups absorbs at very nicely at 1720. From 1650 to 1750, generally 1710, 1720 we observe the carbonyl peak. Then hydroxyl group OH, it generally shows absorption at 3600 centimeter inverse. Second is the fingerprint region. Now, IR, it is also called the fingerprint. IR spectroscopy in itself is called the fingerprint because no two molecules except the enantiomers can have the same IR spectra. Only the enantiomers IR spectra will overlap with each other, otherwise no IR spectra of any compound overlaps exactly as such with the other compound. And in this IR spectroscopy, we also have a fingerprint region. Just like fingerprint is unique to every individual, this fingerprint region is also unique to every compound. Now, the area of this fingerprint region, it is from 1300 centimeter inverse to 687 centimeter inverse, and it is called the fingerprint region. Now, the IR spectrum of any unknown substance compared with the spectra of possible substance, you can identify your compound by keeping your unknown compound or the unknown sample in this region. The pattern of bands in this region, they are dependent on the structure of the molecule as a whole, because single bond peaks also, single bonds also start vibration. Carbon single bond C, C single bond C, C single bond O, C single bond N, they also start vibrating in this region. Therefore, the pattern of bands which is observed in this region, it is dependent on the structure of the molecule as a whole. The region, it is complex because more vibrational peaks are going to be obtained, since both stretching and bending vibrations give rise to absorption here. Otherwise, we were only concentrating on stretching, but in this region both stretching and bending vibrations can be seen. The fingerprint region, it is associated with complex vibrational and rotational energy changes, and it is the characteristic of the molecule as a whole. Since the spectra becomes complex because there are n number of peaks you are going to obtain, but these n number of peaks will give the inside picture of the molecule as to what exactly the molecule is made up of. Therefore, we can easily identify two different molecules by keeping it in the fingerprint region. Now, coming to the instrumentation, a beam of IR light, it is produced and it is split into two separate beams. The one beam, it passes through the sample and the other is passed through a reference, which is often the substance the sample is dissolved in. Now, the first beam passes through the sample itself, and the second, it passes, because there are certain samples, we dilute the samples and then we put in the IR spectroscopy, and the second beam, it passes through the reference material in which we have dissolved our sample or diluted our sample, so that we can study the difference or we can get the exact spectra of our original sample. The beams are both reflected back towards a detector. However, first they pass through a splitter which quickly alternates which of the two beams enter the detector. The two signals are then compared and the printout is obtained. Now coming to the parts, different parts of the instruments. One is the IR source, then the sample cell and the sampling of substances, monochromators, reference and the detector. Here you can see the IR source, one is passing through the sample, then reference, monochromatic system it is there, the splitter, detector and finally the printable readout which we are getting, the spectra which we are getting. The sources, different different light sources we have taken. You can take the mercury arc lamp, tungsten lamp, then nickel chrome wire you can use. So different sources we can take in the system. Sample cells. Now sample containers which are used in the spectrophotometer, such as glass, quartz, silica cuvettes, which are impermeable to infrared lights. Non-covalent materials are transparent to IR light. Thus, NaCl or KBr salt plates are used commonly as the sample containment. Since these quartz tube or cuvettes which are there, they are impermeable to the IR radiation, that means IR light cannot pass through them. Therefore, generally we dissolve a sample. If it is liquid in the sodium chloride, a pouch is made, or if it is solid, it is grinded with KBr, salt plates are made, transparent plates, and then they are put into the IR spectrophotometer. Now the plates are transparent to the IR light and they will not introduce any lines into the spectra. Sample preparation. If the sample is solid, then it is pressed, pellet technique, it is pressed at high pressure to make a transparent film. Liquid, it can be sandwiched between two plates of high purity salts, generally NaCl, and measure the absorbance. Again, gas, if the sample is gaseous, again it has to be taken in the same manner like liquids. Monochromators are used to cut down the light of all other wavelengths. Only a single wavelength light passes through them. Then there is detectors. Generally detectors which we are using are the thermocouples or the bolometers. Recorders to record the IR spectrum. Now coming to the uses and application of IR spectroscopy. Now this IR spectroscopy, it can be used for the identification of functional groups. In the functional group region, we can study or we can find out which exactly functional group is present in the organic compound. Then it is used for determination of impurities in a sample. If the sample is going to be pure, then the peaks, absorption peaks will be clear. Thin, well defined peaks will be obtained. But if there is impurity, then broad peaks are going to be obtained. Shape or symmetry of the molecule can be determined. The determination of force constant from vibrational spectrum, the value of F can be calculated. It provides a valuable information of dipole moment and bond length. Bond length can also be calculated. It is also useful to distinguish positional isomers of a compound. Then it can be used for distinguishing between inter and intramolecular hydrogen bonding in a molecule. The hydrogen bond, whether it is within the same molecule or whether it is taking place between two different molecules, we can find out through IR spectroscopy. Thank you.